Okay, so the Bluetooth is turned in and the voice is fine. So now we will study lecture 3 that will begin the development of the first fundamental theorem, that is the Caratheodory extension theorem, that will actually enable us to create measures on the sigma algebra through the construction of pre-measures on semi-algebras or algebras, you can say. So rho on an algebra or semi-algebra, we can do with algebra only, is set to 0 comma infinity. Okay, let's start with semi-algebra. Is set to be a pre-measure. If it satisfies the properties of measure, but there is a problem because the countable union may not be in S. So we give the property that if it is in S. So if union n equal to summation rho n, if union n belongs to S, then this is called to be a pre-measure. Well, one thing is clear, that given a pre-measure, we can uniquely extend it to the algebra generated by it. So we know that how the algebra generated by AS looks. It is all finite disjoint unions of elements in the sigma algebra, in the semi-algebra. So there is only one way possible to extend, that is define it a disjoint union A in 1 to k lambda, call this rho prime. This is the extension rho prime of this. Well, there is exactly one way to define 1 to k rho ak. We need to show that this is well defined, which is because suppose one set has two representation, 1 to k union disjoint union 1 to m b t, then okay, not k here, let's put it I here and there. So one thing is clear, that rho of ai intersection bt, this is a disjoint collection where sum is over I from 1 to k, j from 1 to m, and this sum can be interchanged. So first sum I to 1 to k, this is summation j equal to 1 to m rho of ai intersection bj, not ai intersection bj, this is this union ai intersection bj. Yeah, so did I write this correct? Yeah. So rho of this, since union ai intersection bj is nothing but union, so is nothing but disjoint union ai. So I am doing something wrong probably. Yeah, so this is actually not this, this is actually bj. Oh, sorry, this is actually bj. So union ai intersection bj for fixed j and all I, this is disjoint union ai intersection bj, but this is equal to disjoint union 1 to m bt, which is bj, and since this is again disjoint, this is rho of disjoint union 1 to m bt, and this is how defined as rho prime. And we can interchange the sum, and doing the exact same thing, we can rho prime disjoint union 1 to k ai. So this sum is well defined, and we can easily check that this defines a pre-measure. So analogously, a pre-measure is defined on an algebra. So it defines a pre-measure of an algebra. So given a pre-measure on a semi-algebra, we can uniquely extend it to a pre-measure of an algebra. The question comes, can we extend to it sigma algebra? And this question is very difficult to answer. So before that, I will give an example of a pre-measure that will not prove. I will refer where to see. So if f is a R to R increasing right continuous function, then define, this is defined on the semi-algebra of that, the God-given semi-algebra that we are given of semi-open closed sets that we did in the first lecture, that we started by speaking in the first lecture. Then lambda f we define a comma b close is fb minus fa. If it is increasing and right continuous, it can be shown that lambda f is a pre-measure, and this we will not show. This is just real analytic techniques, but not quite cumbersome. So lambda f is a pre-measure on S, and this we refer to fallout. Fallout is a good thing. So if lambda f is a pre-measure on S, so if you take fx equal to x, then this gives the God-given length function that we work with, that is a b minus a. So given a pre-measure on f, now we state what the recipe is. So this is the recipe that we are gonna follow. This probably 2 to 3 lectures, hopefully 2, but it may extend to 3. So the recipe is like this. So during when we had rectangles, what we used to do, given suppose an surface, we used to cover it by rectangles. So you would later see that these rectangles, rectangles also form a semi-algebra. So actually product of two semi-algebras is also semi-algebra in the product. So we cover them by rectangles, and we take the area of the rectangles and we take the infimum, and we define the area of the surface to be that. We will do exactly the same process here. So what we will define, so suppose S is a semi-algebra on X, and there is and rho is a pre-measure on S. Then we will define on power set of X a function that is mu of A for all subsets, mu star of A, we will define as infimum of summation rho A n union n covers A, and n belongs to S. This will be known as the outer measure. So this will satisfy some properties, we will see, and using those properties we will define knives. So knives that which nicely act under this outer measure. So suppose there is this space, every space, and we take any space A, then so suppose this is a knife, A is said to be a knife, and for any set E, A and A complement divides its area nicely. What we mean is that mu star of E for all E belongs to A is said to be a knife, if mu star of E is equal to mu star of A intersection E plus mu star of A complement intersection E, and these are called mu star knives. Then what we will do, we will take the collection M of all mu star knives. And first we will show that M is a sigma algebra. And mu star restricted to M is a measure. Second, we will show that the algebra, so we will work with the algebras only, it doesn't matter much. So S or algebra, we can work with anything. So the algebra, so instead of S, if you work with an algebra here, so it's convenient actually, because we know if given a semi-algebra, we can extend it to algebra. So let's work with an algebra only. So given the algebra is contained inside the cell. So all the elements in the algebra are mu star knives, and mu star restricted to the algebra is actually the row. So mu star actually extend this. So this gives an existence of the extension of the measure. So since it contains A, it will contain f of A. So it gives an extension of a measure up to the sigma algebra generated by A. And third, if the pre-measure is sigma finite, if rho is sigma finite, analogously as a measure is sigma finite, so it can be covered by elements in the algebra such that their pre-measure is finite and their union is the whole space, sigma finite, then such an extension is union. And these three are the fundamental goal, and these three is known as, combined is known as the Caratheodory extension theorem. Extension is union. So we will try to prove 1 and other things here, and 2 and 3 we will try to prove in the next lecture. So this is the recipe. So let's start. So outer measure, so mu star is said to be outer measure if it is a map from a power set of x to closed interval 0, infinity. Outer measure if 1 mu star of phi equal to 0, mu star is monotonic, A subset of B implies mu star A less than equal to mu star B, and it's countably subadditive, that is union mu star of union An countable is less than equal to any count sum is mu star of union, sorry, mu summation of mu star, summation of mu star. So first we construct an outer measure using this. So define mu star of a given row, given the pre-measure on the algebra, define mu star of any E, as infimum of summation rho A's, that union A and cover E, and A belongs to the algebra. So this set is non-empty because X is in A. So we take the infimum exists. So first we have to show that mu star is an outer measure, that is mu star of phi equal to 0. So this is trivial because phi is a cover of phi. And 2 is mu, it's monotonic. So if let's call this set to be whose infimum we are taking, call this S of E. So if A subset of B, every cover of B is also a cover of A, so SA contains S of B. So the infimum is smaller, so infimum of S of A is less than equal to infimum of S of B. This implies rho of A, sorry, mu star of A less than equal to mu star. Last one, we use a technique. So we want to show countable subadditivity. So take En a collection. So if one of them is infinite, one of mu star En is infinite by monotonicity, the left side is infinite, the right side is infinite, so it's done. If so, assume everyone is finite. So mu star of En plus epsilon by 2 to the power n. So since it is infimum, this is greater than some summation rho of A J n, where A J n union over J cover En. So takes for every n is to take the sum. So this means summation sorry, this implies summation mu of en plus epsilon. Epsilon is arbitrary, so this is double summation rho a n j. So this is also countable sum, and this is union a n j. Now this covers union n, right? So this thing is greater than equal to mu star of n, and since this is true for every epsilon, the proportion follows. A star is necessary. So we have established that this is actually outer measure. Now we work with the neat ones, that is called knives. So a subset of x is said to be a mu star knife if mu star e equal to mu star of a intersection e plus mu star of a complement intersection for all e subset of x. These are called mu star knives. And now let's prove the first proposition. Well, one thing is clear, that this always holds for all a and all e. This doesn't hold, but one side holds. That is, this holds by countable subadditivity. So it's enough to show the other side. So the other inequality implies that this is knife if it happens for all. Alright. So this is trivial. This is not. So first let's show m equal to all such a subset of x. A is a mu star knife. Then M is a sigma algebra. And mu star restricted to M is a line. So first we show M is an algebra. So clearly, if mu star E is equal to mu star A intersection A plus mu star A complement intersection for all E belongs to F. So since it is symmetric under complements, if A is mu star knife, then obviously A star A complement is also mu star knife. So we need to show it for intersection. Suppose A comma B belongs to F. Then for all E, mu star of E is equal to mu star E intersection A plus mu star E intersection A complement. Then mu star, again since B is there, is A intersection B plus mu star E intersection A intersection B complement. Right, mu star E intersection A complement intersection B plus mu star E intersection A complement intersection B complement. Now you can observe A complement union B complement is nothing but A intersection B complement union A complement intersection B union A complement intersection B complement. So by countable subadditivity, this thing is greater than mu star of E intersection A intersection B plus mu star of E intersection A union B complement, that is A intersection B complement, by countable subadditivity. Thus we are done. Since it was arbitrary, so A intersection B also belongs to it. Now we will show mu star is finitely additive. So suppose En is a finite disjoint collection from 1 to k, 1 to k. Then define disjoint union En from 1 to t to be ft. Yeah, so actually you have to do induction on k actually. So if so mu star of mu star of, let's say, f for any f is mu star of f intersection. So we know En, since it is an algebra, finite, it is closed under finite unions. So we can write this as first E1 plus mu star f intersection E1 complement. So yeah, okay, put f equal to mu star f equal to, put f equal to union 1 to k En, then mu star of En, u disjoint union, is mu star of E1, and since it is disjoint, this is mu star of union 1 to k minus 1 En. Then use induction hypothesis. Right. So the mu star is finitely additive. It can be proved in similar manner, exactly similar manner, that the mu star of f intersection f intersection disjoint union En, where f is any set 1 to k summation mu star of f intersection exactly in similar lines. So mu star is finitely additive. Now we have to show it's a sigma algebra and that mu star is countably additive. So let En be a countably infinite disjoint collection. Define fk to be 1 to k, En to be fk, and f equal to disjoint union 1 to infinity En. Mu star of any set, suppose L, is equal to mu star of L, since it is in the algebra, fk is there, fk plus mu star L intersection fk complement. Since fk is subset of f, fk complement contains f, so by monotonicity mu star of L intersection fk is greater than equal to mu star of L intersection f. By this argument here, we can claim this is summation 1 to k mu star of L intersection En, or this is f complement, plus mu star of L intersection complement. So, and since it is true for all k, by limit 10 tends to infinity, we claim that mu star of L is greater than equal to mu star of L intersection Fk plus, this is equal we know, mu star of L intersection F complement. This is greater than equal to okay, since it is true for all k, we can take k equal to infinity and still it is true. So this is mu star of L is greater than equal to summation 1 to infinity mu star of L intersection Ek plus mu star of L intersection E complement. By countable subadditivity, this is greater than equal to mu star of L intersection E. That is the L intersection. I don't know why I am writing F. This is F and this is F. So mu star of L intersection F complement, and this is greater than equal. This is greater than equal to mu star by countable subadditivity. So all these inequalities will be actually equalities, right? So this shows that if one small mistake I did, well, I assumed En to be disjoint. It's not disjoint. En is non-disjoint. Disjointify En. So take actually Kn. Ens are the disjointification of Kn. So En plus 1 equal to union Kn plus Ki, I from 1 to n plus 1 minus union 1 to n Ki. So En is subset of Kn. Unions are always same. So union En, finite, infinite, doesn't matter, is always same. And then do this. So then repeat the exact same thing. So you have disjointified it. So L. So all these are so okay, I guess my battery went out of this. Okay, fine. So all these here are equality. So mu star of, so put L equal to disjoint union En here 1 to infinity. So mu star of disjoint union 1 to infinity En, that is F here. This is summation 1 to infinity mu star of Ek, and this is 5. So this doesn't prove it. We have shown it is true for disjoint union. So this disjoint, it is finitely additive for disjoint unions, and we have shown that since this holds, since this is equal to this implies mu F is in the sigma algebra, and F is nothing but union of Kns. F is nothing but disjoint union Ai, that is union of Kns. So M is a sigma algebra, and this proposition shows that it is, for disjoint we did, this is countably additive. So the first part is done. We will prove the second and the third in the next part.